All right, good morning, everybody. Series solutions of ordinary differential equations, which, again, I cannot overemphasize how important it is to learn the techniques of dealing with infinite series, power series, Taylor series. Are there any questions about any of the homework problems? Any problems you would like me to do? If not, then let us deal with what are called singular points instead of just what we've been looking at, which are ordinary points. So we're in the following situation. We have a second order homogeneous linear differential equation, P0 of x y double prime plus P1 of x y prime plus P2 of x y equals 0, where these functions, P0, P1, and P2, are polynomials. No trig functions or logs or exponentials. And if they're polynomials, if they have a common factor, we can divide out by it. So they're polynomials with no common factor. And we say that the point x naught is an ordinary point if P naught evaluated at x naught is different from 0. And in that case, around x naught, you can divide by this. You get a polynomial where the coefficient of y double prime is 1. And there's a general theorem that says that such an equation has a unique solution for any initial values at x naught in some open interval around x naught. That's an ordinary point. And when you have an ordinary point, we saw that there's always a series solution, an infinite series solution. That's the first case. But the second case, which is more interesting in some sense, only because it's harder, is when we have what is called a singular point. The point x naught is a singular point if P naught of x naught is equal to 0. And then you can't divide by it. So for example, there are a lot of, in math and in physics and especially, there are a lot of second order homogeneous ordinary differential equations that arise that have singular points. So if you have something like 1 minus x squared y double prime minus 2xy prime plus alpha times alpha plus 1y equals 0 for some alpha. So this is an example of a second order differential equation. Now, this is my P naught of x. And that's equal to 0 if and only if x is plus or minus 1. So for this differential equation, x naught equals 1, x naught equals minus 1 are singular points, because this is 0 at those two values. And for x naught different from plus or minus 1, we have an ordinary point. So if you're trying to solve an initial value problem at x naught, there's a straightforward series method if you have an ordinary point, but it breaks down if you have a singular point. And that's what we want to consider. Okay. Now, mathematics can be very complicated sometimes. And solving differential equations in general is not easy. So you look for special cases that are important by themselves, but where in fact there's some methods for finding a solution. So certain singular points are easier to deal with than others. And this type of singular point we're going to consider now is what is called a regular singular point. So this is section 7.4. It deals with what are called regular singular points of a special type of differential equation, which is called an Euler equation. So this is a famous mathematician from the 18th century whose name is pronounced Euler, like oil, Euler. But that's how it's spelled. So suppose we have a differential equation, P naught of x, y double prime, P1 of x, y prime, plus P0 of x, y equals 0, where P0, P1, and P2 are polynomials. And suppose they're of a particular kind. Suppose P naught can be written as x minus x naught squared times some polynomial a of x. P1 of x can be factored into x minus x naught times some polynomial b of x. And P2 is just another polynomial we'll call c of x, where a at x naught is not 0. So this is the type of differential equation we are considering. Now, this is clearly 0 when x equals x naught, because just get 0. So x naught is a singular point, but it's a regular singular point if this coefficient of y double prime factors into x minus x naught squared times something which is non-zero at x naught. If P1 is 0 at x naught, b of x can be 0 or not 0 at x naught, and c of x is just a polynomial. So this is an example. So this is the definition of a regular singular point. So we say that x naught is a regular singular point if the differential equation can be written in this form. So for example, there is something in physics called Bessel's equation, x squared y double prime plus x y prime plus x squared minus something squared y equals 0, and x naught equals 0 is a regular singular point, because this coefficient of y double prime, if x naught is 0, this just has to be x squared times something. It's x squared times 1. So this is like x squared times 1. This is x times 1. This is whatever it is, c of x. So this is an example of a regular singular point of a differential equation. In the simplest Euler equation would happen when, let's say we take x naught equal to 0. So we have an equation x squared a of x plus x b of x, so y double prime, plus xb of xy prime plus c of xy equals 0. The simplest would be the case when a of x, b of x, and c of x were just constants. So a x squared y double prime plus bx y prime plus cy equals 0. So this actually is what is called an Euler equation. And what we're going to do today is learn how to solve all Euler equations. That's pretty good. Okay. So this is our mission. A different from 0. B and C can be any constants. Ax squared y double prime plus bx y prime plus cy equals 0. And what do we know about solutions of this? So for x different from 0, you could always divide by ax squared. You get y double prime plus bx over ax squared y prime plus c over ax squared y equals 0, or y double prime plus b over ax y prime plus c over ax squared y equals 0. These coefficients, these functions, are non-zero for all x different from 0. So by the general theory, it says this equation has unique solutions on, not at 0, but on the interval from 0 to plus infinity, and on the interval, open interval from minus infinity to 0. So we know from 0 to infinity, for example, this equation always has a solution, and every initial value problem has a unique solution. And for simplicity, we're just going to consider the positive half open, the positive interval, infinite interval from 0 to plus infinity. Such an equation always has a solution. And if you specify initial conditions at some particular point x naught greater than 0, the solution is unique. So let's experiment. Let's try a solution that is just a power of x. Suppose we have y equal x to the r. Right? Remember, when we were looking at first order equations, when we were looking at second order equations with constant coefficients, we look for solutions of the form e to the r. In this case, and we can try e to the r, but nothing comes out very easily. We try just a power of x, and let's see what happens. So if y is equal to x to the r, y prime is r x to the r minus 1. If you differentiate it again, you get r times r minus 1, x to the r minus 2. So let's plug this into this equation. We get ax squared y double prime plus bx y prime plus c y. And now a miracle happens, because we have x squared times x to the r minus 2. So this is a r times r minus 1, x to the r. Here we have x times x to the r minus 1, that's br, x to the r. And here we have c x to the r. And now we see every one of these terms is a multiple of x to the r. So if we factor out x to the r, we get a r times r minus 1 plus br plus c. And we want that to be 0 for x positive, which means this is 0 because x is greater than 0. We're only looking for positive values of x. If and only if r is a solution of the equation AR, r minus 1, plus BR equals C, plus C equals 0, right? If this is 0, x to the r is a solution. And once again, we have a quadratic equation in R. It's not the same as the quadratic equation that came up earlier when we were looking for exponential solutions of constant coefficient second order homogeneous linear differential equations. So this is not r squared, this is r times r minus 1. So if you write this out, this is exactly the same as AR squared plus B minus A R plus C equals 0. So whenever you have a solution of this equation, you should have a solution of our differential equation. Let's look at an example. Let me just summarize that here so I don't have to keep turning back and forth. If we have the Euler equation, ax squared y double prime plus bxy prime plus cy equals 0, y equal x to the r is a solution if a r times r minus 1 plus br plus c equals 0. So here's an example. X squared y double prime minus xy prime minus 8y equals 0. So in this case, A is equal to 1. B is minus 1. C is minus 8. So what does this equation say? This says 1 times r minus 1 plus br, which is minus r, plus c is minus 8 equals 0, where r squared minus 9r oops, not 9r, what am I doing? R squared minus r minus 2r minus 8 is 0. What are the solutions of this? I think this factors. This is r minus 4 times r plus 2 equals 0. So you get r squared minus 2r minus 8. So this has two solutions. R equals 4 and r equals minus 2. So if we take y1 equal to x to the 4th and y2 equal to x to the minus 2, these are solutions of this differential equation. And so the general solution, y equals c1 x to the 4th plus c2 x to the minus 2, or I can write this as c1 x to the 4th plus c2 over x squared. So for any constant c1 and c2, this function is a solution of this differential equation, and this is extremely well defined for x between 0, greater than 0, and infinity. So we solve this problem. Now, you'll remember when we were solving constant coefficient second order equations, there were three cases. We had a quadratic equation, and there are three possibilities. There could be two distinct real roots. That's what we have here. And we get 2 powers of x as the solutions, x to the 4th and x to the minus 2. You could have two solutions that are equal, or you could have two different solutions, but they are complex conjugate numbers. They're not real numbers. This is the case when you have two real solutions. When you have two solutions that are equal, the situation is different. And when you have two solutions that are complex conjugate pairs, the situation is often equal. And let's just do some examples to see what happens. That's really maybe the most straightforward way to go about this. So here again is our situation. We have an Euler equation. We have this quadratic, it's called the indicial equation, but name is not important. Suppose we have this case, x squared y double prime minus 5x y prime plus 9y equals 0. So the coefficient of x squared is a equal 1. The coefficient of x is minus 5. The coefficient of y is c equal to 9. So our equation is r times r minus 1 minus 5r plus 9 equals 0. This is r squared minus 6r plus 9 equals 0. This is r minus 3 squared equals 0. So there's one solution, r equal 3. So y1 equal to x cubed is one solution. What does the other solution look like? There has to be a second solution. It's going to be y1 times the log of x. Or x cubed, I like to write log, but log and ln are the same thing. X cubed equal log x. I claim this is also a solution. So let's check. Let's see if this is correct. y2 prime is 3x squared log x plus x cubed times 1 over x, which is 3x squared log x plus x squared. Or if you like, x squared times 3 log x plus 1. So the second derivative is by the product rule, 2x times 3 log x plus 1 plus x squared times the derivative of 3 log x plus 1, which is 3 over x. So I have, what is this? This is 6 x log x plus 2x plus x squared times 3, this is 3x plus 3x, which is plus 5x. That's y2 double prime. So let's plug these into the original equation and see if we have a solution. So x squared y double prime is x squared times 6x log x plus 5x minus 5x y2 prime is minus 5x times x squared 3 log x plus 1 plus 9y, that's plus 9 x cubed log x. So let's see what we get. Hope it works out. This is 6 x cubed log x plus 5 x cubed minus 5 x cubed minus 5 x cubed times 3 log x plus 1 plus 9 x cubed log x. What we have here is minus 15 x cubed log x minus 5 x cubed. So plus 5x cubed and minus 5x cubed, they cancel. 6x cubed log x plus 9x cubed log x is 15 minus 15x cubed log x These also cancel, so we get 0. So this is correct. And this is the general situation. So in the case of an Euler equation, ax squared y double prime plus bx y prime plus c y equals 0, if a r minus 1 plus br plus c equals 0 has a double root, then double root r, then the general solution is x to the r and x to the r log x. So c1 times that plus c2 times that. That's the general solution for a double root. So what about the third case? In the third case, you have a pair of complex conjugate roots. So let's look at that. So here we have another example, x squared y double prime plus 3xy prime plus 2y equals 0. The coefficient of x squared is a equal 1. The coefficient of x is b equal 3. The coefficient of y is c equal 2. So our equation is 1 times r minus 1 plus 3r plus 2 equals 0. This is r squared minus r plus 3r plus 2r plus 2 equals 0. So you can solve with this with the quadratic formula, or if you like, you can write this as r squared plus 2r plus 1 plus 1, using the fact that 1 plus 1 is 2. This is r plus 1 squared plus 1 equals 0. So r plus 1 squared is minus 1. So r plus 1 is plus or minus the square root of minus 1, which is plus or minus I. So r is equal to minus 1 plus or minus I. So we have two roots. R1 is minus 1 plus I, and R2 is minus 1 minus I. And I claim what will be the solution is, so if you took x to the minus 1, that should be part of it. If we let y1 equal x to the minus 1 cosine of log x, and y2 equal x to the minus 1 sine of log x, let's just experiment. I claim these are solutions. So let me do the calculation and see. So here was my differential equation. And I have one purported solution, 1 over x, or x to the minus 1, cosine of log x, and 1 over x, sine of log x. So let's try the first and see what happens. So this is y1. So what is y1 prime? Well, by the chain rule, derivative of x to the minus 1 is minus x to the minus 2 times the cosine of log x, and by the product rule, plus x to the minus 1, the derivative of the cosine of log x. What is the derivative of the cosine of log x? Minus the sine of log x over x. So y1 prime is minus x to the minus 2 cosine of log x, and x inverse times 1 over x is another x to the minus 2 minus sine of log x. So this is minus x to the minus 2 cosine of log x plus the sine of log x. That's the first derivative. It's differentiated again. The derivative of x to the minus 2 is minus 2x to the minus 3, and minus times minus is plus, so this is x to the minus 3 cosine log x plus sine log x minus x to the minus 2 times the derivative of this. Derivative of cosine log x is minus sine of log x over x. Derivative of the sine of log x is the cosine of log x over x. So I have x to the minus 3 cosine of log x plus the sine of log x. I can factor out 1 over x times 1 over x squared. This is 1 over x cubed, or another x to the minus 3. This is plus sine of log x minus cosine of log x. So these cancel, and this is x to the minus 3, 2 times the sine of log x. So let's see whether this really does give us a solution of our differential equation. So I have x squared y double prime plus 3xy prime plus 2y equals what? So here we're using the solution. Y equals 1 over x, x inverse, cosine of log x. So, and the second derivative, so this is x squared. This was the second derivative, 2x to the minus 3 sine of log x plus 3x y prime here was y prime minus x to the minus 2 times cosine of log x plus the sine of log x plus 2y plus 2x inverse cosine of log x. So what do we get? First of all, we have x squared times x to the minus 3, that's x to the minus 1. X times x to the minus 2 is x to the minus 1, and x to the minus 1. So I can factor x to the minus 1 out of all of these terms. And I'm left with 2 times the sine of log x minus 3 times the cosine of log x plus minus 3 times the sine of log x plus 2 times the cosine of log x. And I have some cancellation, but something is wrong because I have 2. what is wrong? So I have to go back and check what I did. Actually, I'm always happy when I do something wrong because I like to have to go back and check. So let's double check our work. Here was my differential equation. X squared y double prime plus 3xy prime plus 2y equals 0. So A is 1, B is 3, C is 2. And A is 1, B is 3, C is 2. So my quadratic equation was r times r minus 1 plus 3r plus 2, r squared plus 2r plus 2. So r is minus 1 plus or minus I. And I claim that x inverse cosine of log x and x inverse sine of log x should be solutions. So I worked out the derivatives. Let me just double check the derivatives. X inverse cosine of log x. So I differentiate, I get minus x to the minus 2 cosine log x plus x inverse minus the sine of log x over x. So that's minus x to the minus 2 cosine log x minus another x to the minus 2 sine of log x. So minus x to the minus 2 cosine plus sine. So this, I think, is correct. If I differentiate this a second time, the derivative of minus x to the minus 2, is plus 2x to the minus 3. Plus 2x to the minus 3. Cosine log x plus sine log x. Let's see, maybe that's my only mistake. Minus x to the minus 2. The derivative of this is minus sine log x over x. Derivative of this is cosine log x over x. So I get x to the minus 3 that I can factor out. This is two cosine log x plus 2 sine log x plus sine log x minus cosine log x. So what this is really is 2 cosine x, 2 cosine log x minus cosine log x. That's 1 times the cosine of log x plus 3 times the sine of log x. So let's see, I hope this is correct. Let me just double check this again. I get plus the sine, so I have 3 sines. I have 2 times the cosine minus, so let's see if this is correct. So I take this and I plug this into my differential equation. So it's x squared y double prime, which is 2x to the minus 3. And what this is cosine of log x plus 3 times the sine of log x. And then 3x y prime, which is minus x to the minus 2 cosine plus sine plus 2 x inverse cosine log x. So all the powers of x are x to the minus 1. So let's just write this out again. This is x to the minus 1 times 2 cosine of log x plus 6 times the sine of log x minus 3 times the cosine of log x minus 3 times the sine of log x plus 2 times the cosine of log x And still doesn't work out right for me. What is the problem? Anyone see where I made a mistake? I'm 100% sure that this is correct. So why is my arithmetic not working out? So when you make mistakes, the only thing to do that I can think of is start again. Let's start again. X squared y double prime plus 3x y prime plus 2y equals 0. And when we solve the equation r times r minus 1 plus 3r plus 2 equals 0, we get as our solutions, so this is the same as r squared minus 2r, sorry, plus 2r plus 2 equals 0, either by factoring or just by the quadratic formula, you get this is minus 1 plus or minus I. And I claim one solution is x to the minus 1 times the cosine of the log of x. This is always for x positive. So the log is always defined. So y prime is minus x to the minus 2 cosine of log x plus x inverse times the derivative of this, which is minus the sine of log x over x. So this is minus x to the minus 2 times cosine log x plus the sine of log x. I have a minus and a minus and a minus, cosine plus the sine. That looks okay. So the second derivative is minus 2 times this. This is 2 x to the minus 3 cosine log x plus sine of log x minus x to the minus 2 times the derivative of this, which is minus the sine of log x over x plus the cosine of log x over x. So I have an x to the minus 3 in both terms. I can factor that out. I have 2 cosine of log x plus 2 sine of log x plus sine of log x minus cosine of log x. So this is x to the minus 3. 2 minus 1 is 1 times the cosine of log x. 2 plus 1 is 3, plus 3 times the sine of log x. So now let's plug these expressions into our equation. X squared y double prime, I multiply this by x squared, I get x to the minus 1 times this. Three x times y prime, so 3x times x to the minus 2 is 3x to the minus 1. So this is minus 3 times cosine of log x minus 3 times the sine of log x plus 2y plus 2 times the cosine of log x. And now it works, thank God. Excellent. Because I have 1 times the cosine minus 3 times the cosine plus 2 times the cosine. They cancel. And I have 3 times the sine minus 3 times the sine. They cancel. So I had the right solution. I just kept messing up the check. Okay. So let me summarize the theorem, or let me state as a theorem, how one solves an Euler equation. AX squared y double prime plus BXY prime plus CY equals 0. So let's say R1 and R2 are the roots of the quadratic equation. And there are 2 cases. Case 1, R1, R2 are real numbers, R1 different from R2, then x to the R1 and x to the R2 are a fundamental set of solutions to this differential equation. And the general solution is any linear combination of these 2 powers of x. That's when you have 2 real roots. Case 2 is when R1 equals R2 is real. You have a double root. And then one solution is going to be x to the r, let's call this r. And the other solution is going to be x to the r log x. And the general solution will be C1 x to the r plus C2 x to the r log x. And in the third case, we have R1 is some complex number. Let me write it in the notation of the text. R1 is some lambda plus I omega. R2 is lambda minus I omega, where lambda and omega are real numbers, and omega is positive. Right? One is positive. One has imaginary real part positive. The other is going to have the complex conjugate imaginary real part negative. And in this case, your solutions are x to the lambda cosine of omega x and x to the lambda sine of omega x. And the general solution will be any linear combination of these 2. So this is a complete description of the solutions of this Euler equation. So this is a special case, but an important special case of an ordinary differential equation with a regular singular point. Okay. Any questions about this? Okay. So I hope you're following along in your book, because everything in the book is the same and legible. So let's look at some exercises. Exercise number 1 is to solve x squared y double prime plus 7xy prime plus 8y equals 0. So the coefficient of x squared is a equal 1. Coefficient of x is b equals 7. Coefficient of y is c equal to 8. So we have the equation r times r minus 1 plus 7r plus 8 equals 0. This is r squared plus 6r plus 8 equals 0. This factors r minus 2, r plus 2, r plus 4 equals 0. So this equation has two real roots. R1 is -2, R2 is -4. So the general solution for x positive will be C1 x to the -2 plus C2 x to the -4, or if you like, C1 over x squared plus C2 over x to the 4th. Let's check. If this is y prime is -2 C1 x to the -3 minus 4 C2 x to the -5. Y double prime is -2 times -3, 6 C1 x to the -4, minus 4 times -5 is +20 C2 x to the -6. So x squared y double prime plus 7xy prime plus 8y is equal to x squared times 6 C1 x to the -4 plus 20 C2 x to the -6 plus 7x times y prime minus 2 C1 x to the -3 minus 4 C2 x to the -5 plus 8y C1 x to the -2 plus C2 x to the -4. So what is all this? X squared times x to the -4, that's 6 C1 x to the -2. X squared times x to the -6, that's 20 C2 x to the -4. X times x to the -3 is x to the -2. So this is -14 C1 x to the -2. 7 times 4 is 28, minus 28 C2 x to the -4, plus 8 C1 x to the -2, plus 8 C2 x to the -4. 6 and 8 are 14, minus 14 is 0. 20 plus 8 is 28, minus 28 is 0. We get 0. So this checks. So that's the solution of this differential equation. Okay. Any questions about that? Okay. Well, how about this? I'll give you a chance to solve a problem. That's always fun. Let's look at number 3. X squared y double prime minus xy prime plus y equals 0. So A is 1, B is -1, C is 1. We have the equation r times r minus 1 minus r plus 1 equals 0. R squared minus 2r plus 1 equals 0. What are the solutions of this quadratic equation? What are the solutions? Well, this is r minus 1 squared equals 0. So we have a double root, r equal 1. So that says one solution is x to the r, which is x to the 1, and the other solution is x log x. let's check. If y1 is x, y1 prime is 1, y1 double prime is 0. If you plug this into the equation, you get x squared times 0 minus x times 1 plus x is minus x plus x is 0. So that checks. What about y2? X log x, the derivative is 1 over x, is 1 times log x plus x times 1 over x. This is log x plus 1. So y2 double prime is just 1 over x. So x squared times 1 over x minus x times log x plus 1 plus x log x. This is x minus x log x minus x plus x log x. Everything cancels and you get 0. Okay. All right, well, I have a non-responsive group out here today. I don't want to go beyond this section, and this section is fairly straightforward. So the next homework assignment will be problems from section 7.4. And I'll post them almost right away and encourage you to work on some of them. And class on Wednesday, ask me to do any problems you might find more complicated. Any questions before we end for the morning? If not, then we're done. Bye all. Enjoy the day.